Life. It's the most amazing thing we know of. It's a force that has shaped our world for billions of years, creating a beautiful mix of different forms and complexity. But how did it all start? How did non-living things turn into the first living beings? This question has interested scientists and thinkers for centuries, and it remains one of the biggest mysteries in science. Understanding where life came from is not just about being curious. It's about knowing our place in the universe. It's about understanding the complex web of life that connects us all, from the smallest bacteria to the largest whales. It's about seeing the delicate and strong nature of life, and the amazing journey it has taken over time. The search for life's start takes us back to early Earth, a time when our planet was very different. It was a world of great heat, volcanic eruptions, and a poisonous atmosphere. Yet somehow, in this wild environment, the seeds of life were planted. The journey from simple molecules to complex beings is a story of great cleverness and strength, showing the power of evolution. This video will look into the main scientific ideas about how life began. Picture the early Earth, a place very different from the world we know today. The air was a toxic mix of gases, with no oxygen for us to breathe. Volcanoes erupted violently, throwing out molten rock and gases into the sky. The oceans were hot and acidic, and meteorites often hit the Earth. It was a tough and harsh place, but somehow, life began here. To understand how life started, we need to know what early Earth was like. Scientists think our planet formed about 4.5 billion years ago from a cloud of gas and dust. As the Earth cooled, a solid crust formed, and volcanoes released gases that made the first atmosphere. This air was full of methane, ammonia, water vapor, and carbon dioxide, but it had no free oxygen. The oceans formed when water vapor cooled and fell as rain on the cooling Earth. These early oceans were hot and acidic, dissolving minerals from rocks and creating a chemical-rich environment. This primordial soup had the building blocks of life-simple organic molecules like amino acids, nucleotides, and sugars. These molecules, the raw ingredients of life, mixed and reacted in the ancient oceans, setting the stage for the first living organisms. One of the oldest ideas about how life started is the primordial soup hypothesis. This idea, first suggested in the 1920s by Russian chemist Alexander Oparin and British scientist J.B.S. Haldane, says that life began in a mix of organic molecules in the early Earth's oceans. They thought the energy to form these molecules came from lightning and ultraviolet rays from the sun. In 1953, Stanley Miller and Miller-Urey, scientists at the University of Chicago, did a famous experiment to test this idea. They recreated the early Earth's conditions in a lab flask, filling it with water, methane, ammonia, and hydrogen. They then used electrical sparks to simulate lightning. Amazingly, after a week, they found amino acids in the flask, which are the building blocks of proteins. The Miller-Urey experiment was the first to show that the building blocks of life could come from non-living matter under early Earth conditions. It was a big discovery, exciting both scientists and the public. But the experiment also had its limits. It didn't show how these simple molecules came together to form more complex structures, like proteins and nucleic acids, which are needed for life. Despite its limits, the primordial soup hypothesis is still a key idea in the study of how life began. Scientists are still looking into the chemical reactions that could have made more complex molecules from the primordial soup. They are also studying other energy sources, like hydrothermal vents, which might have helped life start. While the idea of the primordial soup talks about life starting on the surface of early Earth, another interesting idea says that life might have started deep in the oceans, around hydrothermal vents. These vents are cracks in the ocean floor where hot water comes out, full of minerals and chemicals. Hydrothermal vents create special places full of life, even without sunlight. Chemosynthetic bacteria, which get energy from chemicals instead of sunlight, are at the bottom of the food chain in these places. These bacteria live on the chemicals coming from the vents, making a lively spot in the otherwise empty ocean depths. The conditions around hydrothermal vents might have been perfect for life to start. The vents give a steady supply of energy and chemicals, and the porous rocks around them could have acted like tiny reaction chambers, helping molecules come together to form more complex structures. Also, the high pressure and temperatures near the vents could have sped up chemical reactions, possibly leading to the first self-replicating molecules. RNA world hypothesis, the dawn of genetic material. The primordial soup and hydrothermal vent ideas give possible ways for life's building blocks to form. but they don't fully explain how these molecules turned into self-replicating entities, which is a key part of life. This is where the RNA world idea comes in. This idea suggests that RNA, not DNA, was the main genetic material in early life. RNA, like DNA, can store genetic information and act as a template for making copies. But unlike DNA, RNA can also act as an enzyme, speeding up chemical reactions. This dual role makes RNA more flexible than DNA, and it has led scientists to think that RNA may have come before DNA in the early history of life. In an RNA world, RNA molecules would have carried genetic information and helped with their own replication. Over time, DNA, which is more stable, may have evolved from RNA and taken over as the main genetic material. Proteins, with their many roles in speeding up reactions and building structures, would have evolved later, becoming the main workers of the cell. The RNA world idea is supported by several pieces of evidence. For example, RNA is found in all living things, playing key roles in making proteins and other cell processes. Also, some viruses use RNA as their genetic material, suggesting that RNA-based life forms may still exist today. The Great Oxidation Event, a turning point in Earth's history. The early Earth's air had no free oxygen, very different from the air we breathe today. This changed a lot around 2.4 billion years ago, with the Great Oxidation Event, when oxygen levels in the air went up quickly. This event had big effects on life on Earth, allowing more complex organisms to evolve. The GOE happened because of cyanobacteria, tiny plants that make oxygen as a byproduct. As cyanobacteria spread in the oceans, they released a lot of oxygen into the air. At first, this oxygen reacted with iron in the oceans, creating rust that sank to the ocean floor. Once the iron was full, oxygen started to build up in the air. The rise of oxygen had a big impact on life. For many organisms that lived without oxygen, the GOE was a disaster. Oxygen was poisonous to them, and many died out. But the GOE also created new chances for life. Organisms that use oxygen for energy evolved and thrived in the oxygen-rich environment. The GOE was a turning point in the history of life on Earth. It marked the end of the world without oxygen and the rise of life that needs oxygen. It allowed for the evolution of more complex organisms like plants and animals, which need oxygen to live. From simple cells to complex organisms, the rise of biodiversity. The first life forms on Earth were simple, single-celled organisms like bacteria or archaea. These early cells were prokaryotes, which means they didn't have a nucleus or other complex parts. They were also anaerobic, meaning they got energy from chemical reactions instead of oxygen. Even though they were simple, these early cells were very tough and could adapt well, setting the stage for the wide variety of life that came later. Over billions of years, life on Earth changed and became more diverse. About 2 billion years ago, a new kind of cell appeared, the eukaryote. Eukaryotic cells are more complex than prokaryotes, having a nucleus and other parts that help them work better. Eukaryotes probably evolved through endosymbiosis, where one cell takes in another, and they both help each other. The evolution of eukaryotes was a big step forward in making life more complex. It allowed for more advanced cellular processes and led to the evolution of multicellular organisms. Multicellularity, where many cells work together to form one organism, happened multiple times in different groups, leading to the evolution of plants, fungi, and animals. While the ideas we've talked about so far focus on life starting on Earth, another interesting idea is that life might have come from somewhere else in the universe and traveled to our planet. This idea is called panspermia, and it has been around for a long time, but people have become more interested in it in recent years. Panspermia suggests that life, in the form of tiny living things or even complex organic molecules, could have traveled on comets, asteroids, or even tiny dust grains in space. These space objects, hit by cosmic radiation and carrying pieces of the early solar system, could have acted as vehicles for moving life across the vast space. One of the most convincing pieces of evidence for panspermia is the finding of organic molecules, including amino acids and nucleobases, in meteorites. These meteorites, pieces of asteroids that have fallen to Earth, give us a look into the chemical makeup of the early solar system. The presence of life's building blocks in these space objects suggests that the ingredients for life may be common in the universe. While the idea of life coming from space is fascinating, it doesn't mean that life couldn't have started on Earth. It just broadens the possibilities, suggesting that life might be more common in the universe than we once thought. Looking for life beyond Earth is one of the most exciting and tough jobs in science. If we find signs of life on another planet, it would change how we think about the start and growth of life, both on Earth and in space. It would mean that life is not just something that happens on Earth, but is a basic part of the universe. Scientists are looking in many ways to find life in space. One way is to look for planets that go around other stars, called exoplanets, that might have the right conditions for life. These conditions include having liquid water, a stable air, and a source of energy, like sunlight or heat from the planet. Another way is to look for signs of life in our own solar system, especially on Mars and the icy moons of Jupiter and Saturn. These moons, even though they are different from Earth, might have places where tiny life forms could live. For example, Mars might have had liquid water on its surface in the past, and it still has ice under the ground that could support tiny life forms. Looking for life in space is a big job, but it shows our endless curiosity and our wish to know our place in the universe. Whether we find life elsewhere or not, the search itself helps us learn more and makes us value the special and delicate life on Earth. The start of life is one of the biggest puzzles in science. We have learned a lot about early Earth and the chemical reactions that might have created life's building blocks, but many questions are still unanswered. Scientists are still working on these puzzles using a mix of chemistry, biology, geology, and astronomy. This journey is driven by our natural curiosity, our wish to know where we come from, and our wonder at the amazing phenomenon of life.